Okay, welcome. So what we're going to be working on today is a lecture on fluid dynamics. Now, we'll get into this, but I do want to just give you a heads up. The main two things you're going to want to know about this content are going to be the continuity equation and the Bernoulli equation. But first thing I want to talk about what fluid dynamics is, and then sort of get into these equations and then hopefully do an example of it. Well, basically what this is motion of fluids. Now, it turns out that we're going to be looking at an even more simplified view of fluid motion than we did for motion of uh, of of solid objects. So the idea is that in motion of fluid, you have lots of different types of motion. And the one we're going to focus on is laminar flow. And basically, what this means, one, it means the fluid is flowing in more or less a uniform fashion. And it means that the edges of the kind of the vessel that's containing the fluid aren't affecting the motion much. So, like I say, this is kind of like the equivalent of ignoring friction. When you have very small microfluidic channels, you get into what is called parabolic flow. And this has to do with the I can't write, parabolic flow. This has to do with the fact that the edges slow down the fluid motion. And that has because the channel ends up being so small, that has a significant impact on the overall motion of the fluid. So you have this gradient of fluid velocities throughout the channel that the thing is flowing through. Now, that's not something we're going to look at. And then there is, of course, turbulent flow. Um, and turbulent flow, basically, this is what happens when you have the fluid starting to do these kind of weird motions, just in the context of this fluid of this vessel flowing. So laminar flow, basically, all the fluid is flowing in one direction at more or less a constant velocity. Turbulent flow, this is where the fluid starts to mix itself up, and you get these spinning little eddies and currents and things like that, and within the motion of the fluid. So this can happen. It can happen, rather routinely. And it turns out the math behind turbulent flow is actually pretty hard. It's actually extremely hard. It's one of the most difficult areas of theoretical areas of physics. So we're definitely not going to be doing either turbulent flow or parabolic flow. We're going to be sticking to laminar flow. These are sort of the building blocks that you start from when you want to go when you want to build up to these more complicated areas. So, like I said, we're going to be basically focusing on two different equations in order to solve things. And again, when you have a fluid flow problem, I'm focusing on this because essentially what you're going to do is you're gonna probably write down these two equations and figure out what you know and what you don't know, and then use the equations in tandem to find what you're looking for, basically. So the first one is the continuity equation. Now, basically what this is, the way I want you to think about this is conservation of mass for fluids. And when we're doing fluid dynamics, we're going to also be dealing with incompressible fluids. So basically liquids. And for the most part, we're looking at flowing water. We're not really looking at really anything else. We're not looking at gases. The fact that, pressure can change the density of a gas, that's a complication that we're not going to add, just because we're doing things that are, like I said, fluids is a class that you could it could be it can be an entire class. We're just looking at the very simple case. So that simple case is going to be incompressible fluids, which, like I said, is going to basically be water. And the idea behind this is that the way you can think about it is, what we can have is we have, some fluid, flowing this way. And you'll see a lot of this in diagrams. You'll see these lines. These are called fluid flow lines. They indicate the direction, and then the how compact the lines are. That sort of indicates the speed of the fluid, so the speed in meters per second of the fluid. But this is basically what we're going to be looking at. Now, what I'm going to do is I'm going to say, okay, what we have right here, I'll just do, we can imagine this is like a pipe. This will be my in circle, and then I'll have a purple right here, right next to it. This will be my out circle. Okay. So the idea behind conservation of mass, and I'll change colors, is that the mass into the red circle, it has to be equal to the mass out of the purple circle. Okay. And that is basically where the continuity equation starts. And the whole idea is that, you make these circles close together, these two rings that you're basically looking at. You make them close together, and from there you can essentially say, okay, what this is going to mean is it's going to mean that mass is not neither created nor destroyed between going into the red circle and coming out of the purple circle, so they have to be the same. Okay, so that's basically what we're going to say. Now, the idea that this is occurring in a static system means that in this case, the mass going in per unit time into the red circle has to equal the mass coming out of the purple circle per unit time. So the way we would write that is we would say m in per delta t, whatever that delta t happens to be. This has got to be equal to m out per delta t. Okay, so that's the way that's going to look right there. All right, so that's what's happening right there. Now, from here, what we can do is we can actually start treating like a little block of fluid in here. So basically what we have is I'm just gonna make this little red block delta X, and I'm gonna make this little purple block that will be called that delta X out and delta X in. Okay. And the idea is that the way I've drawn this, these will actually be the same. But basically, the idea is that fluid moves delta X in delta T. That's the idea. Now, why am I doing that? Well, because now what I can say is that I can say, okay, the volume in times the density of the fluid over delta T. Remember, that's just using the density formula. Density equals mass per unit volume. So I just replace mass with volume times density and on both sides of this equation, and that's essentially what I'm going to be doing right here. So that would be density times the volume out per delta T. Now, this is where having the fact that this fluid is incompressible is useful. And the way we can do that is density is a constant. If we're doing flow of something like air and the density can change, then we can't do this next simplification. But if density is constant, these two will cancel out, and we're just left with the volume in over delta T equals the volume out over delta T. Now, I'm leaving that delta T. We could also cancel the delta T's, but we're going to see something. We're going to see something here in just a minute. Now, the volume in, and again, you can think about the volume in as being this little red cylinder that I've drawn here. And we could say, okay, there's a cross-sectional area in and a cross-sectional area out. So the area, this is the cross-sectional area of the pipe. All right. And the reason we're going to need this is because we're going to use that to find the volume in terms of a couple of things we know. Okay. So the reason is that this delta X can kind of be as long as we want it to be. Like we could, if we increase delta T, that would increase delta X. but the cross-sectional area of the pipe, at least in this case, is going to be constant. And in any case, the cross-sectional area is a constraint of the system, even if it changes. So even if you have a pipe that gets wider or gets more narrow, that is a constraint of the system that the fluid will naturally adapt to, okay? So it's not a property of the fluid, it's a property of what's constraining the fluid. So that's why we're defining this. But the whole point is then that your volume is equal to your delta X that I've drawn up there times your A. Now, the whole idea behind this is that now what we can have here is we can have delta X in times A in over delta T. And then that will be equal to delta X out times A out over delta T, where those delta T's are still just the same. Now we're going to use one last simplification here, where that delta X in over delta T, that's just the velocity in. So V in. Now, this is one case where it can be a little confusing. I'll try to make this a big V and then a lowercase v. This is the velocity of fluid in meters per second. Okay. So this is one way you can do this. Now, when you have this, then you replace. So that was velocity in, and then area in, and then this is equal to velocity out times area out. And basically, what these two things are, the velocity in times the area in, we call this Q in, and then that equals Q out. And what Q in this case is, Q, this is what we call the volumetric flow rate. And all this means is it's just a volume per unit time, okay? So the idea behind this is that for anywhere in a pipe, we can draw like one of these cross-sectional area circles, and we have to say that the volume flowing into that has to equal the volume coming out of it, okay, per unit time. The volumetric flow rates at all points in the pipe have to be equal. That's basically what the continuity equation is saying. So I'll state that. Continuity equation says volumetric flow rates at all points in the pipe are equal. Okay. Now I've shown that for a very simple example, but this example is also kind of simple, but let's just say we have a pipe that does something like this. Okay. Now you can imagine this would be like the end of a syringe or something like that. Okay. And what you end up having here is if you have these flow rates, what they need to do is they're spread out initially, which means they're going kind of slow. But when they come together, they have to compress, which means they go faster. Okay. And this continuity equation helps us to figure that out. So what we could do is we could just draw two circles, and this would be the in circle, but this time the out circle is going to be significantly smaller. Okay. And the idea is that A in is greater, whoops, that to be black, is greater than A out. Okay. So the whole point is that this is going to have a consequence. Now, if you've ever used a syringe, you probably know that the result of this is that the fluid flows faster when you're coming out here. And the continuity equation is how we determine how much faster. Okay. So the idea here is that if we have Q in equals Q out, well, we need to remember that the volumetric flow rate is just the speed of the fluid times the cross-sectional area, and then that will be the speed of the fluid out times the cross-sectional area out. So the idea here is that if we want to define the out velocity, it's equal to the in velocity times the ratio of the areas, okay? So the fact that A in is greater than A out means that V out is going to have to be greater than V in, okay? So they increase, the velocity increases in proportion to how small the area, the cross-sectional area of the pipe becomes, okay? And you can kind of if you've ever played around with a hose, which I'm sure many of you have, you can kind of get a sense of how this works. So if you just have a normal garden hose, the water's coming out pretty steadily. If you wanted to squirt somebody and get it to go a lot faster, what you do is you cover up part of you don't cover up the whole thing, but you cover up part of the hose. You basically make an improvised nozzle. And what that does is it makes the opening much smaller, which increases the speed as it's coming out. Okay, so that's fundamentally what is going on with the continuity equation. All right, so the main continuity equation that you want to remember is that A1, and I was just calling that in, but really it's just at a particular location. A1 V1 equals A2 V2. And this can be at any point in a fluid flow situation. Okay, so that is the continuity equation that you're going to want to have to use. All right, next one, the next equation to talk about is the Bernoulli equation. And what the Bernoulli equation is, this is conservation of energy. Okay, sometimes this thing does not like to work. The Bernoulli equation is conservation of energy. And I'm going to make a slight note. It's conservation of energy density for fluid flow. Okay. Now, why do I say conservation of energy density instead of just conservation of energy? Well, the idea, again, going back to why we use density instead of mass for fluids, is that the fluid is not, it's a continuous system, all of which is kind of moving at the same time. So it's hard to say, okay, how much energy is in the whole thing. It's much easier to quantify the energy in terms of something per unit volume, and that is exactly what we're going to be doing with conservation of energy here. Now, deriving the Bernoulli equation is somewhat difficult. You can do it. I'm not going to do that here, but basically the idea is what you would need to do is you would need to consider three ways that energy that a fluid can basically have energy. So the three, and I'm just going to call this types of fluid energy. The first one is kinetic energy. And again, we'll do kinetic energy density. Now, you know that the formula for kinetic energy is 1/2 mv squared. For kinetic energy density, it's just going to be 1/2 rho v squared. Where this time, again, the v is the speed of the fluid. Okay, so it was the same thing that we just were talking about in the continuity equation. But now it's being used to describe the kinetic energy that a fluid can have, and this is one type of energy that a fluid can have. And then another one would be potential energy. Now this is going to be you will have seen this formula before when we were dealing with static fluids, but this is going to be rho GH. Now, as a reminder, this is the same. So H is the height above a 0 point, height above 0 point. This is the same as the fluid pressure of a static system. Okay. And the idea here is that the more fluid pressure you have, basically the harder this fluid is pushing, and the more, in the right circumstances, the more speed you could turn that fluid into. Now, because of the way fluids are constrained, you can't always convert that into speed. So sometimes what you have is you instead have this potential energy density. A situation like this would be like a dam, where you build up all the water behind the dam, and basically you're storing potential energy in all that water, and you're only letting a little bit of it out So not all that potential energy is being converted to kinetic, but you're doing it at a very specific rate. Okay, so that's what's going on there. And then finally, there is the work done on fluid. And basically, the way this is quantified is it's quantified as the fluid pressure. Now, this is a little bit more difficult to see, but what I just want to show you something really quickly here. And the way we can think about fluid pressure, this is also a work per unit volume. And the idea here is that if we have some pressure over here, as a reminder, this pressure is going to be equal to force per unit area. If we then do a work, if we were then going to try and find a work, work is equal to the force times some delta x. So basically this thing would go some delta x like so. And again, this is hopefully this is looking somewhat familiar there. But we can then say, okay, the work is then, subbing in force was equal to pressure times area. So work is equal to pressure times area times delta x. Well, remember what we said, this A delta x was equal to above. This was just equal to a volume. So work is equal to pressure times volume. The volume of this, this little block that the fluid has moved due to the force of the pressure. So it would be pressure times volume, and where that's volume, by the way. And then we can just say, okay, the pressure is the work per unit volume. So work per unit volume. All right. So these are the three types of energy that we're going to have to deal with. 1, 2, 3. And the idea behind Bernoulli's equation is that the overall or the combination of these three energy densities will be constant in a fluid flow system. All right. So what does this mean for Bernoulli's equation? So the whole point of this is that I wanted to give you some sort of background and make some connections to something we've seen before, just in terms of conservation of energy. But Bernoulli's equation is coming now, and it's going to be kind of similar to the continuity equation, where we reference two different points, any two different points in the fluid flow system. The product of area times speed had to be equal at any two different points. Similar sort of thing is going to be going on with the Bernoulli equation. Okay. And so for the Bernoulli equation, what you have is you have P1 plus 1/2 rho V1 squared. So this is at location 1 plus rho G H1. So these are all at location 1. And basically, that's just going to have to be equal to the sum of things at location 2. So that's going to be equal to P2 plus 1/2 rho V2 squared plus rho GH2. Okay. So that is what I was this is going to be at location 2. All right. And this is the Bernoulli equation that you will want to be using. So this is the second one right here. So these are the two equations that you're going to want to use to solve these problems. All right. Now, I wanted to do a couple of examples with this. So that's what I'm going to do now. All right. So this will take a little bit longer, but hopefully these examples will be useful. Okay. So this one is just an example from the textbook. Now this is and and this was why I part of the reason why I gave I should probably put this up here. Q in equal or Q1 equals Q2. And again, remembering that Q1 and Q2 are the volumetric flow rates, because sometimes that's what you're given instead of a fluid speed. And this is an example of this one. So it says a nozzle with a radius of 0.25 centimeters attached to a garden hose with a radius of 0.9 centimeters. The flow rate through the hose and nozzle is 0.50 liters per second. Calculate the speed of the water in the hose and in the nozzle. Okay, so this one is basically what you're relying on here is you have to know that the flow rate is equal to the area times the speed. Okay, and you got to get your units right. So my advice is get everything in SI units. Okay, because if you do it just this way, you're gonna wind up with problems. Okay, so R1, that's 0.25 centimeters, that's 0.0025 meters. I'll do 2 off to the side here. R2 is 0.009 meters, so 9 millimeters. All right, and then Q1 is going to be equal to Q2. So Q is 0.500 liters per second. Now, the how I would do this, what you want this to be, and you want this to be in meters cubed per second. There are other ways to do this. So yeah, I mean it's that I would again I would get everything in SI. Okay, you can if you're clever, you can get the units to cancel out in particular ways, but getting everything into SI is quite helpful. So I'm gonna show you how to get something from liters per second into milliliters per second. So hopefully those will make or into SI units, and SI units would be meters cubed per second. So and eventually you can just remember the conversion, but I'll show you how I would go through the process if I didn't remember it. Liter per second. All right. So first thing I would do is I would say, okay, 1000 milliliter per liter. Okay. So this would then be 500 milliliter per second. Now, one thing to remember is that 1 milliliter is equal to 1 centimeter cubed. Okay. That is just something you kind of need to remember. It's how you go from the exclusively volume to the length-based metric. There are other ways, and we'll talk about another one that's probably just going to be easier to remember in a minute. But in any event, that's how this would be. So this would be equal to 500 centimeter cubed per second. Now, hopefully you remember that 1 meter cubed is equal to 1 million centimeters cubed. If you don't, you can verify that again, but that is what we're gonna have here. And so what we end up with here, this becomes 0.0005 meters cubed per second. Okay. So the other way you can remember this is that 1 meter cubed equals 1000 liters. If that helps you to remember it, then that's fine. But and you'll notice that if we could have just done that conversion directly, which would have been dividing this initial thing by 1000, and that would have gotten us to the same thing. So either way, remember one or both of these two conversions. Okay, so that's going to be useful. All right, now that we're in SI, we can find our velocity in meters per second. Okay, so what we have is we have Q is equal to A1 V1. Now, as a reminder, A1 is pi R1 squared because it's a circular cross-sectional area. It's a radius we were given. So we have 0.005 is equal to 0.0. I did not include enough zeros there. 0.005, 0.025 squared times pi times V1. Okay. And then to solve for that, you would just have V1 equals 0.0005 over 0.0025 squared times pi. And then you find whatever that is. Now, V2, somewhat similar in that the Q is the same, okay? And that's what they're getting at by only giving you one flow rate. It's a reminder that the flow rate is the same. So it's still just 0.005 meters cubed. But this time we're going to use the second radius instead of the first one. So this would be 0.009 squared times pi. And you can calculate both of those. Okay. I'm not gonna go ahead and do that and waste your time on that, but you can go ahead and do that. That is how you would solve this one. All right. So this here would be the nozzle because that was the smaller radius, and this here would be the hose. Okay. So I do that one basically involves the continuity equation and the fact that flow rate is equal to cross-sectional area times velocity. Those are that is the main idea there. Now I want to go grab a problem on Bernoulli's equation. Okay, so this one I want to talk about because this is going to use all aspects of the Bernoulli equation. And sometimes people have a hard time identifying the appropriate values to use in various different aspects of this. And you need to be really careful about doing this correctly. So the main idea is that is similar to how we were doing how we oftentimes had to infer quantities from the way the problem was phrased in in things like kinematics and with forces. We're going to have to do something similar here. Okay. So this question says, what is the pressure drop due to the Bernoulli effect as water goes into a 3 centimeter diameter nozzle from a 9 centimeter diameter fire hose while carrying a flow rate of 40 liters per second? To what maximum height above the nozzle can this water rise? Okay, so this is actually well, it's really going to be looking at three different situations. I'm going to try and draw this so you can see kind of what's going on. What we have initially is we have a hose here, okay? So, and then very similar to the problem we just did, what we have is we have a narrowing into a nozzle, okay? And so we could view the hose as case one, the nozzle as case two, and then we have this thing is going up, and I'm going to draw it. Really, it's vertical. It should be vertical. That's what we're really looking at here. But I'm going to draw it kind of sideways just so we can see kind of what's going on. And then the idea here is we want to know, okay, what is this height? So this would be 3 and this would be the maximum height. Okay. And what this means is we're going to be looking at least 3 different situations here. Okay. Now, what we're given here, we're only given, I'm going to do this without bold. So our hose, and I'm going to just call that R1. Okay. So I like to categorize these things as situation 1, situation 2, situation 3, just so I can keep what's going on in mind. That's 0.003 yes, meter. No. 0.03 meters. And then the R of the 0.09 meters. That was the nozzle. R of the nozzle, which would be R2, would be 0.03 meters. Okay. Now I would also calculate just while I'm doing this. I know that I don't want to accidentally use R instead of A. So I would just say that A1 is 0.09 squared pi, and A2 is 0.03 squared pi. Now, the setting this up, what you might be able to check out, and sometimes the ratios we'll get to in a minute, but but you might be able to see that when you set up a ratio, the pi's will cancel, and it turns out that that some other nice things will happen. The fact that the radius is 1/3 in the nozzle means that the area will actually be 1/9, and you can verify that using a number of different ways. But if the nozzle radius is 1/3 the hose, then its cross sectional area will be 1/9, and we'll you can calculate that out if you want. But what I would do here is I would say, okay, Q is going to be equal to A1 V1, and we got to find V1. We got to find V1 first. Okay, so as a reminder, Q is 40 liters per second. Now remember, 1 liter is 1,000 liters is 1 meter cubed. So this would be 0.04 meters cubed per second. Okay, meter cubed is pretty big. So a lot of these flow rates will be decimals in terms of meter cubed. So one of the reasons liters per second instead of meters cubed per second is used. But when we're doing calculations, we want to convert to SI. Okay, so we have 0.04 meters cubed per second is equal to 0.09 squared pi, and that would be meters times V1. So V1 is equal to 0.04 meter cubed per second over 0.09 squared pi. And I will go ahead and do that calculation. When we find that, we get 1.57 meters per second. Now we can find V2 using using A2 and V2 instead of that. But I actually think it's a little easier to do A1 V1 is equal to A2 V2. And what we're going to get is we're going to get V2 equals A1 over A2 times V1. So A1 over A2, as I reminded you, what that's going to be, that's A1 is going to be 9 times as large as A2, and you can verify that if you want, but 0.09 squared pi over 0.03 squared. What we could do is we could just realize that this is basically the same as 9 squared pi over 3 squared pi. That's just, taking a ratio. And the pi's will cancel, and you'd have 9 squared over 3 squared, which would be 81 over 9, which would be just 9. So V2 is going to be 9 V1. So I just think it's easier because then, I've got V1 already in my calculator, and I get 14.1 meters per second. Okay, now the idea here is that what we're going to do is now we want to know the pressure drop. Okay, so we have the two volumes, or the two speeds. Now we want to know the pressure drop. To get the pressure drop, we've got to use Bernoulli's equation. So as a reminder, that's P1 plus 1/2 rho V1 squared plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. Okay. Now, the idea here is that when the hose compresses from the wide to the nozzle, we're going to say that functionally the height hasn't really changed. Okay. So basically, we have H1 and H2. And we're just going to basically say H1 equals H2, whatever that height happens to be. Now, if H1 equals H2, then these two terms are equal, which means they'll just cancel. Okay? So they will just end up canceling out like that. And what you end up with is you end up with P1 plus 1/2 rho V1 squared plus P2, equals P2 plus 1/2 rho V2 squared. Now we want the pressure drop. So pressure drop, basically, the way you can think about it is when fluids move faster, that results in a drop in pressure. There are a number of different ways that this can happen, but basically the way you can think about it is you're burning up some of that stored work in the form of pressure in order to increase the speed. That's what's going on there. Okay, so we would have P1 minus P2. That is the pressure drop. And we can see that if we rearrange this equation, we subtract the P2 from both sides. We can also subtract the kinetic energy term from both sides, and we end up with 1/2 rho V2 squared minus 1/2 rho V1 squared. So this is what we're trying to calculate. So we just have 1/2 rho and then V2 squared minus V1 squared. And then calculating that out, as a reminder, rho is 1,000 kilograms per meter cubed. Anyhow, we want this all to be in pascals. So we have 1/2 times 1,000 times 14.1 squared minus 1.57 squared. Okay. And plugging that in, squared minus 1.57 squared. And then times 0.5 times 1,000. And what you end up with is 98,838. Really would be 800 pascals. That's 3 sig figs, or 0.988 kilopascals. Okay, so not 0.9. 988 kilopascal, 98.8 kilopascals. I do not know why I can't convert there. Yeah, you'd move it 3 places to the right, it'd be 98.8 kilopascals. Okay, so that's the drop you had there. Now, the maximum height. We can do this 2 different ways. Now, basically what I would do is I would say, okay, I'm going to do it between points. I'm going to scroll back up to here, between points 2 and 3. Now, the reason I'm going to pick point 2 is because we already know that we can also think that this is the pressure when leaving the nozzle. Or sorry, 2 is the situation when leaving the nozzle. Okay, so when leaving nozzle. All right. So the idea here is that what we can say about the pressure at point 2, we can say the pressure equals 1 atmosphere. And that's basically because it's left the confinement at this point. And the only thing confining this stream anymore is just going to be the atmospheric pressure. And the pressure at 3 is also 1 atmosphere. So the whole idea is that going back down to here, it should have been pressure 2. It might have written, yeah, pressure 2 is that pressure 2 equals pressure 3. Now, why is that relevant? Well, when we set up Bernoulli's equation, P2 plus 1/2 rho V2 squared plus rho GH2. That's going to be equal to P3 plus 1/2 rho V3 squared plus rho GH3. Well, there are a couple things that will happen. One, if P2 equals P3, these two are equal, then these two just cancel. Okay, so that's one thing. The other thing is that what we can do is we want to know how high it goes above the nozzle. So we can basically set H2 is equal to 0. Okay, now if H2 is equal to 0, basically this is just the starting height. So that means that term vanishes as well. Okay, so that was how we got that term to go away. Now, the last thing we can do is we can also say V3 equals 0. Why? Well, this goes back to kinematics. And remember, basically, once this fluid stream leaves, it's going to, go up, slow down, slow down, slow down, until it gets to the top, and then starts coming back down. Now, the idea there is at the top of that arc, that is where its velocity is equal to zero. Okay, just like a projectile. At the maximum height, the velocity is equal to zero. So what this means is it means this term vanishes right here. Okay. And now what we have, you'll notice we have something that's very similar to just a maximum height using energy equation, or even a maximum height using kinematics equation. Okay. So what we end up with here is we just end up with 1/2 rho v2 squared is equal to rho g h3. Now we cross those out, and then we can find h3. Just h3 is going to be v2 squared over 2g. And that's something you've seen before, like when finding the maximum height of a projectile, it was just the initial velocity squared divided by 2 times gravity. Okay, so that would be 14.1 squared divided by 2 divided by 10. And this is going to be approximately 9.94 meters. All right. So that is how you would find that one. Okay. So some of these Bernoulli equation problems can be a little bit tricky. And I think one of the hardest parts about it, like solving this algebraically is not too bad. One of the most difficult parts is being able to identify from context which of these terms are zero and which terms will cancel out. So P2 and P3 weren't zero, but the fact that they were equal meant they canceled out in the Bernoulli equation. And then realizing that, oh, I can just set H2 to be equal to zero, okay? Because that was my initial height, and I want to know how much higher above that it goes. I can just set H2 to be zero. That's another key point there. And then lastly, going back to kinematics, I realizing that V3 is going to be zero for this equation is another big thing you need in order to solve that. Okay, so a lot of these things we didn't know in the Bernoulli equation, but a lot of them we can figure out from context. And that is going to be one of the main things to do. So as you're approaching these, write down the continuity equation, write down, the flow rate and how that relates to continuity, and write down Bernoulli's equation. And then again, try and treat it like it's a Sudoku puzzle where you've probably been given some things you aren't aware of, and see which of those things are one going to be zero and two going to be equal to each other, so they'll cancel out. Okay, so that is the main thing that these problems have going for them. So I'm going to go ahead and end things there. I will post this as soon as it's recorded. Your homework on this stuff won't be due until after spring break, so just keep that in mind.